Hey everyone, welcome to today's Explainer. Today, we're diving straight into the core of how energy moves in our universe by unpacking the mechanics of chemical thermodynamics. Specifically, we're going to examine the invisible forces shaping the physical world around you, all through the lens of exothermic and endothermic reactions. Have you ever wondered why a roaring bonfire feels intensely hot, but those instant chemical ice packs are freezing cold? Well, it all boils down to how molecules behave and exchange energy with their environment at a microscopic level. That everyday experience of hot and cold is exactly the scientific dynamic we are decoding today. Okay, let's dive into this. Here is our syllabus for today. First, we'll look at the energy around us. Then we'll break down exothermic reactions, where energy goes out, followed by endothermic reactions, which take energy in. After that, we'll break down energy curves, and finally, look at some real-world energy reactions.
Section 1. The energy around us. Heat, light, and electricity.
To really understand these reactions, we have to establish a golden rule of chemistry. Absolutely every single chemical reaction involves a transfer of energy. When molecules rearrange, nothing happens for free, right? Now, we usually default to thinking about heat, like cooking a meal, but reactions can also absorb or release light. Think of a snapping glow stick. They can involve sound, like a booming firework, and they can even involve electricity, which is literally what's happening inside the battery of your device right now. Reactions are dynamic events, constantly trading forms of energy. Moving on to Section 2, exothermic, energy going out and heating up the surroundings. For this section, we are focusing entirely on reactions that actively throw energy outward. We call this exothermic, a chemical reaction that releases energy to its surroundings. A really great trick to remember this is the Greek prefix exo. It sounds a lot like exit. So whenever you see exo, just visualize energy exiting the chemical system and rushing out into the environment. Because of that, if you were to measure an exothermic reaction with a thermometer, the temperature goes up. The reaction is literally generating and pushing heat energy out into its immediate surroundings. The chemical energy that was quietly stored inside the reactants gets actively converted and released as outward heat and light, which is exactly why standing near a burning fire warms up your hands. Let's look at some examples. We've got the obvious ones: burning wood in a bonfire, exploding fireworks with all that heat, light, and sound, and cellular respiration, which is your body breaking down food to keep you warm. Now, what's really interesting about this slide is freezing water and condensation. It sounds totally counterintuitive because ice feels cold to us, right? However, from a strict thermodynamic perspective, going from a liquid to a solid requires chemical bonds to be rigidly formed. And because making bonds releases energy, the act of freezing is, surprisingly, an exothermic process. All right, let's flip the script for Section 3, endothermic, taking energy in and cooling things down. We are pivoting to the exact opposite process here. Endothermic reactions are chemical reactions that absorb energy from their surroundings in order to take place. Think of the prefix endo as meaning into or internal. Energy is actively being taken into the system from the outside world, and it needs a continuous supply of that external energy just to keep going. So thermometer check. In this scenario, your thermometer is going to show a distinct drop in temperature. Endothermic reactions pull heat from their environment to fuel the chemical change. And because they're sucking up ambient heat from the surrounding air, the water, or even your skin, those surroundings lose heat. That's why they feel noticeably, and sometimes sharply, colder to the touch. Photosynthesis is a prime example of this. Plants simply cannot manufacture glucose unless they are continuously absorbing light energy from the sun. Cooking food is another one. Raw rice won't cook unless it actively absorbs heat from boiling water. And just like we learned that forming bonds releases energy, breaking them requires an energetic input. To melt a solid block of ice or boil water into steam, you literally have to force energy in to tear those molecular bonds apart. So melting and boiling are purely endothermic processes. So the crucial point is really seeing these two concepts side by side. It reveals this perfect symmetry. On the left side, in an exothermic process, heat is released, the surroundings get warmer, and molecular bonds are made. Over on the right side, in an endothermic process, heat is absorbed, the surroundings get cooler, and molecular bonds are broken. Getting a firm grip on this dichotomy is the true foundation of chemical energy. Let's move to and see how this builds into Section 4, breaking down energy curves and visualizing the unseen data. When we visualize an exothermic reaction on an energy chart, we start on the left with our reactants.
They are packed to the brim with stored chemical energy, so they start high. As the reaction happens, it releases a massive chunk of that energy out into the world. Because that energy permanently exits the system, our final products on the right end up with a much lower energy value. Basically, it's a high start and a low finish, simply because the energy was given away. Contrast that with endothermic energy levels. Here, our reactants start off quite low on the energy scale. To make this reaction happen, it's kind of like pushing a heavy bike up a steep hill. They have to absorb a massive amount of energy from their surroundings just to get moving. Because they take that energy in and store it, our resulting products end up much higher on the energy chart than where they began. So a low start and a high finish.
And finally, Section 5, Real-World Energy Reactions. Let's test your knowledge a bit. Let's apply these concepts to categorize a few real-world examples. First up, photosynthesis. Since a plant takes light in, the reaction type is undeniably endothermic, and the primary energy form is light. Next, think of a roaring fireplace furiously giving off heat and light. That means it is strictly exothermic. Finally, an instant cold pack. It actively pulls heat away from a sprained ankle, absorbing it. Therefore, it's endothermic, and the primary energy form being transferred is heat. And this brilliantly illustrates a super practical tip for reading chemical equations. If you're looking at a complex equation, just locate the word heat or energy. If heat is written on the left side, the reactant side, it means heat is a required starting ingredient being actively absorbed, making it endothermic. But if heat is written on the right side, the product side, it means heat was successfully produced and released, making it exothermic. Pretty simple, right? To wrap up our explainer today, I have a challenge for you. I want you to apply this science immediately. Just look around your room right now. Whether you're sitting under a glowing light bulb, digesting your food through cellular respiration, or sitting near a warm computer venting thermal energy, what specific energy reaction is happening in your space right this very second? Chemistry isn't just trapped in a textbook, guys. It's the dynamic, energetic world you live in every single day. Keep questioning, keep observing, and we'll see you for our next explainer.